Okay. Good afternoon, all. Again, welcome to Machine Learning for Material Sciences. I think we have covered why this course syllabus, what is machine learning, what is particularly the learning part in machine learning, some mathematical concepts, and last class we covered like Python, why Python, and one of the libraries NumPy. Yes, a little bit crash course. Yes. So now we move on to some of the very basic algorithms that are very popular in machine learning as such. And even if they might not be, matlab, eventually you will be using all these algorithms, but even if they might not look like you are directly using them, most of the other algorithms that you will be eventually using them kind of depend on these algorithms. Yes. And of course, another thought process is like these algorithms help us also me to make you understand some of the things. They might look like super easy, but they are supposed to be easy so that the other concepts of machine learning can just look better. Yeah, excellent. So with that, the five algorithms that we'll be covering is basically linear regression, logistic regression, uh, decision tree learning, and support vector machine, and k-nearest neighbor. And you can like all the five algorithms are basically on the supervised algorithms. That means you have been given a input vector as well as the output labels for those vectors. Yes, fine. So today we'll start with linear regression and we'll see if there is time to cover logistic, then we'll also cover logistic and so on and so forth as the class goes ahead. So now like linear regression. So linear regression would be like it's a super popular regression algorithm that basically learns a model which is like a linear combination of features of the input sample. Okay? And so what is the problem statement we have? So we have a collection, let's say, of labeled examples. So here labeled examples are basically because it's supervised in nature. So we have, let's see if I, yes. So we have a collection of labeled examples like xi, yi, and xi, like, please forgive me for the usage of xi in that sense. It should be like bold xi because it's a vector. And here n is the size of the collection, like, or the size of the number of samples, and xi is the d-dimensional vector, d-dimensional feature vector of example I. Then yi is the real value target. Yes, so because this is regression, I hope you remember, so we have classification, regression, multi-class classification, and then ranking. Yeah. So because this is linear regression, we are targeting regression as such, where the output would be like a continuous value or a real value. Yeah. And here every feature xi is also a real number. Yes. From each of the dimension 1 to d is also a real number. Yeah. So what is the goal then? So the goal is to do this. So goal is to find out a model. Yes. F, let's say wbx, which is equal to wx plus p. Yeah. So, and like here, W would be a d-dimensional, again, a d-dimensional vector of parameters, and B is a real number. Yes. And the notation FWB, whenever we use in the future, it will just mean that it's a model. Let's say you can read it as model F parameterized by two like values W and B. Yes. And what we will do with it. So anytime a new example comes, let's say X new, we'll use the FWB to predict the new, for the label for the X new. Yes. And if the W and B differ from one model to another, there, of course, it is most expected that the F, which is parameterized by two different sets of W and B, will likely produce two different values of Y. Yes, it might not happen also, but expectation is that if the parameters differ, the models itself differ, and the output that they produce also differs. Yes, and uh, what is the goal here? And the goal here is to find out W star and B star, that is the optimal values of W and B, which can predict the actual, like the real or the ground labels. Yes, or which can make the most accurate predictions. Yeah. Now, if you look at this, and I hope you remember the SVM model, yes, we discussed about the SVM like in the first class, yes, like the second class, of course. So what did we do? So it's just very similar of Wx plus b notion, except there was a sign out of this equation, right? There was a sign of Wx plus b. Yeah. So it's very similar. Uh, in the sense of the mathematical concept behind it. The only difference was in SBM, if you remember, there were two different classes, and we wanted to find a hyperplane which basically serves as a decision boundary, which basically separates those two groups of values, right? Positive, negative class, they should lie on one side, and the other negative class should lie on the other side. Yes. So, and the goal was to find the maximum margin. So the decision boundary has to make sure that they are like the decision boundary itself has to be far away from examples. Yes. Otherwise, the equations look more and similar to the SVM. But in this particular case, in linear regression, we want, remember the other hyperplane that we found out, it has to be the maximum, like we were to supposed to maximize the margin. So it has to make sure it lies in some place where it is far away from both the systems. Yeah. Now, but in this case, we want the hyperplane in the linear regression so that this Wx plus b, so that it is close to all the training examples, right? So it has to be as much as possible. It has to be close to the examples. There we are trying to divide those two groups. Here, given all the points, we are trying to sit in the middle. Yes, as much as close. Example is this. Yes. So if we had a bunch of points, I hope you can see the blue examples like the training set. We could have a linear regression that's a particular line which has to be as close as possible. In SVM, we would try to separate them as two groups to be separated. That's a classification problem. Yes, but this is regression. Now, this, if example, so you can see if we had a X new, like, okay, so all the blue points are our training examples. The Wx plus b that we have found out is the linear regression fit here. And if we had to predict for a new X new, what you had to do is just find out at this particular X new where what is the corresponding Y new for it. Yes. And of course, if there is just one dimensional, then we get a line. If it's two dimensional, we will get a plane. And if d dimensional, we just will get an hyperplane. Yes, and I hope you are able to understand like why in SVM we are trying to make sure there is a separation, and in linear regression why we are trying the hyperplane to be as close to examples as possible. Yeah. So of course, like we want them to be as close so that y new also will be more correct to the actual value, or that prediction will be correct. Yeah. So now what do we do? So now that we have done this setup, we have training examples and this one, and we assume that we want to find an hyperplane that is closer to the points. So the goal is to make sure that we find the W and D, right? So that we want to find the W star and the B star. And then for to find W star and B star, we have to run through, let's say, an optimization procedure, which given starting like a random values of W and B, it gives us the closest W star and B star, yes, which can optimize this particular function right now. Okay. The expression, we will come to this expression a little bit, but this expression that we have, if you look at the second line, that's called loss function, yes. So the loss function is just the yi is just the actual label, and fwbxi is the predicted label. Yes, so based on the values what fwbxi gives, xi as an input to the fwb, we get something that is predicted out of the function, and yi is the actual label. So subtracting these two and making it square, for right now, this particular thing is called loss function. In this particular instance, it is a squared error loss, and there could be any other thing also, but the entire concept will be that concept of that function is called loss function, and in this particular instance it is squared error loss. Now all the model based, like anything that depends on some kind of model, they will have a loss function. Yes, and what we want to do is we want to minimize, let's say, the loss function or the objective. Yes, objective will come back to this, and whatever we want to minimize is the cost function. Yes, So the cost function or the objective function is like the C is WB is equal to 1 by n, then summation of I2 1 to n. And this is exactly same as the loss function. Yes. So this particular cost function is called average loss here, and or otherwise you can tell it as empirical risk. Yes. All these are like other names for it, like cost function, objective function, average loss, empirical risk. They could mean separately in other situations, but in this particular case, empirical risk is same as average loss for us, is same as cost function. Yes. And of course, like this is found out, and I is equal to 1 to n, and 1 to n are all the samples in the training set. Okay, we'll slowly cover what are training, of course, yes. And the next step is like why then, so okay, so just going back, linear regression, it is a regression form. The yi has to be a real value, and the one that we have to optimize is wx plus b. What we want to find out is w star b star. We saw what is present, what is not present. For that, we want to design a loss function. So current loss function is a squared error loss. And what we want to do, like as an objective function, we want to minimize is our average loss or empirical loss or the cost function itself, which is basically averaged over all the training set. Yes. Now the question is like, why is this loss function a squared error loss? Why can't it be just fwxi minus yi, right? That could be a question that comes up. Of course, like the answer is sure. Okay, if you have that question, answer is sure. Y square, why not cube? Why not to the power 4? Why not to the power 5? Why not to the power 6? Answers, like the my answer to all of these questions are, of course, we can. Yes. Now, then the next question which should come, like what if, and if all these like the square and cube and to the power 4 to the power 5, if all these are like so much arbitrary, then what do we choose? Yes, anything could work. Yes. Um but so let's go ahead with this one, like for linear regression per se, and what is squared error loss is most general. We of course could use a square or some other polynomial to combine this value of features. Yes. We could also use some other loss function, absolute loss and cube loss, or maybe binary loss we can use. For example, only if it matches with yi, then we will say it 1. Even if it misses by 0.98, let's say the answer was yi should be 1, but our prediction was 0.98, but we'll still mark it as 0. And only if we predict 1 and the actual value is 1, then only we will take it as correct. Yes, that also we could have done. Like all these different decisions about the form of the model, form of the loss function, and what algorithm, and what should we minimize, should we minimize the average or loss or not, everything that we keep on making choices, we will end up with a new machine learning algorithm. Yes. So then the goal is basically designing new machine algorithms should be then super easy. Just find anything that could be changed, should work. But then the point is the scope of entire algorithmic space can be infinite, right? So to square y square, I can do it to the power 1000, right? How much you will try. Yes. And just because you can design a new algorithm does not mean it will work, right? So the goal behind designing or inventing new algorithms will be two things, right? So first of all, we have to understand that the new algorithm that we find out, like the square or so let's say 4 here, we are concerned about the error or the loss function. If we design such a new one, like choosing 3, we hope that it will solve some practical problem that we are facing with the linear regression with the squared loss. Or otherwise, there are other ways to look at it also. So for some example, let's say going to the power 10, let's say, gives us like way better theoretical guarantees. Yes, sometimes for like theoretical guarantees, we have to take some assumptions. With those assumptions, and like even if it does not perform really well, but at least theoretically we understand that we can find some bounds or something, then it's fair. Yes. And most of the times when we design like linear regression and the squared error loss or something, is that we just choose it because it's simple, nothing else. Like, why should we complicate our life? Just use something simple. Hopefully that works and things fit. And most of the times also, if we see in our life, for example, majority of the things, and also there is majority which does not, but most of the times, like we have a good linear relationship. I'm not saying in terms of scientific stuff, but majority of real life, right? So if people start buying more houses, the rate of houses will increase, right? If people start buying more food from one shop, the shopkeeper should be able to reduce the price based on the scale of operation, right? So this looks like a very linear relationship. Most of the general terms are linear, so generally this works, yeah. And we will talk about overfitting and underfitting a little bit later, but as a well right now, yes, this much. Now that we have linear regression and we understand that there is a loss function which is squared error loss here, and the goal is to optimize this objective functions which is average loss over all the training samples, yes. Now how do we do that? And one of the example, okay, so another thing, sorry, I just forgot. So this particular squared error loss, we could also use absolute value, but absolute value has an issue. For example, it does not have a continuous derivative, huh? So the function is not smooth in first order space, and definitely if they are not in the smooth, then like choosing some kind of optimizers like gradient descent and others will be very hard to do so, yes. That is one reason to choose a squared error loss. And another reason to also choose a squared error loss is, for example, compared to, let's say, absolute value, is that if you make a mistake, the more mistake you make, we should penalize you even further, right? So that's why we use square. So for example, a difference of 1 will be 1 because that's squared, but a difference of 2 will give us a penalty of 2 square, right? 4. So we want to highly penalize bigger losses, right? So we want you, like the model should be such that it should make minimum losses across all the training samples, right? It should not be like one major big hole and then like big error in one of them and then try to smooth out rest of them. That will not work here. Yeah. What if your requirement was that? Then that's a different story. You will pick so. Fine. So this is about cost function for now and why the error loss is squared error loss. And then we can design an algorithm for doing this optimization. One of those algorithms is gradient descent algorithm. It's super popular. We will cover some of the parts today. Most of the parts that require a little bit more fancier stuff later, way later. So here what we can do is we can start with a random W and B. So the goal is to do this. W, X and B is the function. The goal is to optimize this particular cost function. So what we do, we start with random W and B. We will then compute gradients. Then we will update the gradients based on whatever our loss is. Yes, whatever the cost function will give us, we'll do this average loss across all the training samples. Then we'll find, okay, so to reach to that particular path, the gradient is this, and so we will update. And instead of updating it full time, because maybe we'll find in training sample it keeps on pulling this side or keeps on pulling that side, we'll update with some like some rate at which we'll update. That particular rate is alpha here. That particular rate is also known as learning rate. So we don't learn at a stretch like a full gradient, but we learn it at a small gap, right? So that we don't overshoot ourselves. But we'll come and talk this, and we can continue to repeat this until convergence. Yes. So till our W and B, they basically don't change, we can continue, or we, even if we don't want to wait till not change at all, we can continue till it satisfies some portion, right? So as in it's below, let's say, some epsilon value, then it's fine. The change in the weight is not that much, the change in the B is not that much, so we will just stop here. Yeah. Now, what will be the advantage of such a linear regression model? Of course, like it's super simple. I know it's Wx plus B, and interpretable because I can just tell, sure, just because this W was high, uh, because let's say your age was, let's say, 20, and like the weight associated with the age was also high, let's say 10, then overall value becomes around 190. So I can tell, so probably your age is what the factor that decided why you got this y. Yes, we could easily tell or interpret why the algorithm, the linear regression, gave you that particular y. Yes, and it's rarely overfits. I told you, like, rarely overfits in the system like general problems that we have, but it also overfits and underfits will come. But it generally matches to the whatever the output we are looking to, and it is super fast to compute. It's just wx, just a clean matrix multiplication, then addition, scalar addition, and we can also have closed form solution for this one. And I hope closed form solutions are known. Closed form solutions are basically if we simply have a very simple algebraic expressions, and we don't have to run through numerical optimization methods. Yes, linear regression has that, but that also depends on something. So, but we can still use gradient descent to solve these problems. Yes. Uh, Now, the next question, I think we have, particularly put emphasis on inductive bias 2 classes ago. And the reason is this. So what we want is in linear regression per se, I will keep on asking these questions to you. The core assumption here is the relationship between the features and the target is linear. Yes, this is something that come from your domain knowledge, right? So if you understand that whatever mapping I'm looking from x to y, if the relationship is linear, then of course linear regression would be a great choice. Yes, because our doesn't matter what the data is, it will still look for linear relationship. Yes, so definitely, as I told you, it is super good for housing prices. Like for example, as the size increases, as the location is closer to some like really fancy place, or the number of like rooms increases in the house, the price will increase. But it is also super bad for problems which do not have a linear relationship. For example, is XOR. Yes, and for example, image recognition. Yes, just because you have too many black pixels, let's say, in the image, does not mean it's always a blackboard. Yeah, or just because it has too much green doesn't mean it's like trees and all this stuff. It's not linear related, right? You'd have too many trees. You can just have a like flag, green flag. Yes, that does not tell how many trees you have. So there are places, or there are situations where the relationship is not linear. There we understand that applying linear regression will not work, and where the situations are linear, so we'll apply. So I know this will be super easy till now, linear regression, but I hope you have touched the more important points. What is inductive bias? That's the choice that we take when selecting an algorithm. Next thing is what is cost function, average loss, empirical loss, um, and loss function. Why do we choose a particular loss function? Most of the times answer is it's very simple. Yes. And sometimes the choice is like we want to penalize mistakes in a higher order, like mistake of 1 is just 1, mistake of 2 is 4. Yes, you cannot make large mistakes. So with that, we will jump on to a minor implementation today. Yes, I will show you, I'll just work out a few example of linear regression today, and hopefully that will give you some view on how to approach. And every class will include something similar. Yes, and as we go ahead, some of the things I will remove. So today we'll do very basic. Yeah. Give me just 1 minute. I'll just shift to. Okay, fine. Okay. I hope this is visible to all. Fine. Okay. So I hope you remember. I hope you remember this particular thing. This is like an VS Code. Inside VS Code, we have a interactive notebook. Yes. And then we have selected our kernel. the same kernel that we selected is just basically an environment that we are choosing. And currently that environment is Python based, and we have installed some stuff. Yes. And the way to install, like, for example, give me a minute. So initially, when you open your like terminal should look like this, like your and the right hand side should come as base, or left hand side will come as base depending on the shell you use. We have to move you activate the environment that you are planning to use. Now that you have been MLMS test, you can install packages or run programs that will use this particular environment. Yes. And one of the packages that we studied last class was NumPy. The other package that we would like to install is something called a scikit-learn. Yes, most of the general algorithms that we'll be doing, at least till neural network, will be based. We can use scikit-learn, and once you install, of course, just press an enter. It will start downloading stuff. I have already installed, so it says all the requested packages already installed. Uh, Otherwise, it might end up giving you errors. Yes. But anyways, it will tell you that the package is not installed, then you have to install. Yes. I hope we are here. And then here, if I did not have anything, it will ask me to either enter code or markdown. So currently we are just doing code. Yes. Excellent. So now we can just give a goal. So initially what we want to do is we have a bunch of X and bunch of Y, uh, and they are mapped together. Okay, so we have X, which is a multi-dimensional vector, and we have Y is a single, just a real value, and which has continuous value. It is not 0 and 1, right? So it has continuous values. So, and then our goal is to find a function f, which will basically map X with Y. Yeah? And what we want to do is also, you remember the note example. Yes. So here we will basically train on some examples. Sorry. You will train on something. This one we can ignore for right now. This is an autocomplete. Sorry, just ignore for now. So note and train. So train is basically the examples based on which we'll be optimizing our W and B. Test is where we will be checking the remaining parts. So we will use some portion of the generated data as our train, and some portions will keep it as test. Yes. And I have iterated multiple times. You are not supposed to see test ever. Yes. The moment you see the test, it becomes training as well. Yes. So now the initial goal is to create the data set X and Y. Fine. Today will be a little bit like from the beginning, so that you can also do it for on your own. Yes, later. Now, okay, so the first is basically what we did was we imported two libraries. Of course, NumPy is there for doing vector operations, and then matplotlib is there for plotting this various diagrams. Yeah? We will use them as we go ahead. Then remember we imported, like we installed scikit-learn. Scikit-learn in the in the package per se, it is also called sklearn per se. Uh, it is sklearn when gets installed. And sklearn is very different from scipy. So those two are different. Whenever you are installing, try to install scikit-learn, not scipy. Scipy will be installed with the scikit-learn, but both are not the same. Hmm. Now we have to create data set. Yes. So okay, so here I have basically the code completion on. So some of the things will be written. Okay. Data sets. Okay. So the first goal is to create a data set for linear regression. Yes. That means we want to create X and Y, and then we'll take it forward. So we can use sklearn basically, and it has something called make regression. So the way this is written is basically sklearn is the bigger package, like, or the bigger library. Under that bigger package, there is a sub package called datasets. Under datasets, there is a one subclass called make regression. Uh, I hope this is clear. So when I import NumPy, I am importing everything that NumPy has. But here I'm trying to import very specific thing because this has been modularized for me. Yes. So I want to go to sklearn package. Under that package, there is datasets, and under that package, there is a, let's say, module or a class called make regression. Okay. And module and class, if this seems new, start studying Python as I mentioned in the last class. Yes. So there is a function called make regression, and we can also do this. And now that we have done two things, so here I have imported datasets, make regression, and train and test split. I will come where these are used. Yes. Uh, okay. So now what we want to do is we want to make the dataset for regression. The way to do dataset for regression will be like this. So I can create, let's say, X and Y thing. And if you see, it is automatically filling this up for me, but I will just explain what it is. So I'm creating X, I'm notioning as capital, but Python does not require it, but it's just for our sense. Whenever I create a capital X, that means like it's a probably a vector, and Y, that means it's just a variable or a scalar that contains only one dimensional values. Yes. And there is a function called make regression because this is something I imported. I'll be passing some inputs to it. Okay, so these inputs are based on whatever this function is. Yes, and samples, that is how many number of values are you creating. Let's say 100 here. Number of features, let's say currently is 1. We are not creating a multi-dimensional X, but rather a one-dimensional X because it is just easy for us to showcase on the figure. What is the noise we're adding? So because we are making regression, by regression it is automatically doing a linear fit here. Instead of that, we are saying okay, add some 10% noise or something, so it will look okay. And random state, currently don't have to worry, but the moment you vary random states, the data set that is created, that means this xy pair that is created, will vary as you go. Fine. Matlab, if you make it 43, you will get a different set of x and y. If you select 44, 96, you will get a different set of x and y. Yeah. So now another thing that we want to do is we want to separate what is like training and what is testing. Give me a minute. Yeah. So those who have used Python, practice some Python, we can do this thing. So we have another function called train test split. This is the one that I imported again from sklearn, but there is another module under sklearn called model selection, and it has something called a train test split. Yes. So I have train test split here. It will take input as x comma y, and then what is the test size? So here I'm telling you reserve 20% for test and rest all can be in training. Training is the one that we'll be using to basically optimize our W and B. And random state is of course like 42. We're just saying how do you split? If you random state is 43, then that split becomes different. Yes, that is basically a random number we are selecting based on which it has to. The moment it splits, it generates these four variables for us, and we are capturing those four variables here. So we have a x train, x test, y train, and y test. Basically, x test and y test will contain the 20% of original x and y, and x train and y train will contain original 80% of the values. Yes. And the goal is to make sure that we are not going to how do I say, we are never going to use x test or y test to train the data. Yeah. So the next is we have mm, yeah. Let me just do yeah. Now here, what you can do is sklearn is one of the libraries that is very useful, and from sklearn itself, let me give me a minute. Yeah, we can also like let's say we can visualize the data set. Yes, so we'll see. Let's say how the data set are coming. This is just showing up. Yeah. So the moment we run this one, just close this terminal for now. Yeah. So it's basically saying like, okay, I created this numpy, then imported this, imported make regression, made trend trace split. I just created dataset X and Y with the make regression function. I added 10% noise. It has only one feature. And I then split it into train and test, because only some part of the data I want to look at while training and some part of data I don't want to, I will test. I'll evaluate my model that I created on the test dataset. But you can also see that they are, because we are doing training and testing, a split on the same dataset distribution that was used, right? Uh, so that is important. Yes. Also, otherwise model will fail very badly. Uh, Now what we are doing is, this is just a matplotlib thing. So we want to use a scatter plot. We are basically adding label of this X label and Y label, and then we just have a title. It's just doing a code fill up, but does not. And plt.show basically shows you the diagram that you have. Yes, we are just doing a scatter plot of X comma Y. Fine. Excellent. I hope there are no questions till now. Okay. What we have done till now is just we have created the dataset. That's all. Fine. Now we go ahead and we will see that how do we find a function f, like which can basically map x to y. Uh, Initially, let's do with like sklearn. So sklearn is a big library that provides all the machine learning models and all this. So we can do this, the linear model. Right? Okay, we did two things here. So I hope, let me just pull it up. Yeah. So now I have sklearn here. What I'm doing is, under sklearn, there is something called linear model. There are a bunch of linear models. One of those linear models is linear regression, the one that we studied just now. And there are something called metrics. Okay, metrics is basically something that we use to decide which algorithm is better or bad. One of those metrics is called R2 score. We will discuss on R2 score in some time, but I assume that is one of the metrics. I will come to that when it comes. Now what we do is, from the sklearn we have imported the linear regression. We can design something called a model. Yes. And we can say, okay, now the model will be linear regression. What do you have to do? You can use the model to fit. Let the model be fitted on train and X train and Y train. Yes. So this is basically a very nice, easy way to find the model. Like, what is the optimal value of W and B? Yes. The one method that we studied, gradient descent, we'll come back to that, but we are using sklearn's own algorithm, let's say, whatever is it has implemented. That algorithm is there in the fit function. And while using the fit function, it will just train. Yes. So after this particular thing, the moment I write model.fit xtrain and ytrain, that means it has already found something. Yeah, that means that already the model, the linear regression that was the original, if you see, sklearn was linear regression. I created a model out of those linear regression, and then I fitted that particular model to the xtrain and ytrain. Yes. Now at this particular moment, once this runs, my model has the value, the correct value, let's say for the W and the B. Yes. Now what I want to do, I want to predict what it did. Right. So let's say I have prediction, but I will do prediction on the X test, right? Because anyway, from the X train, I don't want to, but whatever was my X test, I hope you remember this one. So I distributed between train and test. We trained it on X train, and we are using X test to predict the Y. Fine. And then we can compare the Y that we predicted versus the Y that was actually there. Yes. Now what we can do is, uh, okay. Okay. Fine. Just quickly, sorry, code completion is there. Don't worry. You are also free to use code completion. If you understand everything, it's fine. Yes. Otherwise, you stop. Yeah. R2 score, I will come back, what I said, but the moment what we want to look at is this visualization. Visualization is again the same thing as matplotlib library. Here, what we are doing is first is I'm doing a scatter plot of x test and y test, and then another scatter plot of x test and y prediction. Okay, so x test is y test was our original data that is there in the blue. All the blue values are our original. So given a particular x, I have this blue is the actual one. Given this particular x, this blue corresponding y is the actual y. Then so on and so forth. Yes. What I'm also doing is I'm doing a scatter plot with x test and y prediction. This y prediction came from our model, the model that we fitted on the training set. Yes. So it created its own W, its own B, and based on that FWB, it is predicting the Y. So if you see, it is for the same X, if you look at the X values will be the same, and you will have a for every particular blue, if you see like a perpendicularly, there will be a corresponding like a red color. Red color is the one that we predicted, and of course, like the blue is the original one. And if you see, of course, the blue does not lie in a line closer to a line because we added a noise. All the red have to lie on a line because we are picking the values only from the regressed, like whatever the line that we found out from the model. That is our model. Yeah. And rest all are just these are our information on the coloring signs and everything. As soon as you learn matplotlib also, you'll be able to do so. Yes. So I hope this much is clear. If there are any questions, you can please type. But the major goal here, what I wanted to show you was you can use NumPy. Fine. Specifically, it is useful. Acha, we did not use NumPy here till now. My bad. But Matplotlib to visualize the results. sklearn is a bigger library. We can use various functions, make regression, train test split, and we also use the linear regression function from the linear model. There is one metric R2 score. I'll come to that. And we can use simple model is equal to linear regression, then model dot fit. It will automatically find W and B for us. Then it can just predict X test and Y test. Sorry, it can predict the Y predictions. And then we can compare the difference between Y prediction and X test. Yeah. So that's all we have. And then we can also visualize like this. That will be very useful when you do, right? So I hope now if you have a problem with you, after this class, of course, and going over and repeating, you can apply linear regression on top of it and visualize, okay, this is the case. Yes. Now the question will be, thank God this is one dimensional you have chosen. What if we chose 50 dimensional? Of course, visualization won't be a solution. So then how do we judge? Then we'll end up with something called metrics. Yes. Then metrics are super useful, right? So because if we have like a super high dimensional input feature, here we have just taken one X and one Y. That's why it's super easy. But if we had like a very huge dimensional X and X, then of course you cannot do a plot, finding a hyperplane and plotting them. Like it will be very difficult. To solve that problem at that high dimension, we use something called a like this R2 score. And R2 score, the maths of R2 score, let me see. Let me see if it can write it for me. Okay, I had it somewhere else. Yes. So R2 score definition is this one. So R square is like 1 minus yi minus yi cap and then minus y cap minus yi. So what does this basically means that how far are you from the mean? That's what it says, right? So like if my baseline model just predicts the mean, right? So that is super easy, right? I will take all the y values and I can just predict the mean. But that is mostly not a very good solution, right? Because y actually varies, right? So otherwise y being mean doesn't make sense. So it's you can judge your model at least in linear regression, how regression specifically problems with this R2 score. And if R2 score is closer to 1, that means it's a really nice prediction. We're basically hitting every time. Yeah. And or otherwise, if it is 0, then like it's super bad, like it is as good as predicting mean. It can be negative also. That means it is even worse. Wherever we could have predicted just the mean, it is even going worse than that. Yes. Uh, Variance and everything we will talk a bit later when variance comes. For today, this much. So R2 is just another metric, specifically useful when you have a very high dimensional thing and you cannot plot to just see where are the differences lying. Here I can understand, okay, red is here, blue is here, okay, they're close by, maybe close by, close by, close by, close by. So I can say high dimensional, you cannot just draw hyperplane and find out. Okay. Fine. So this much is clear. We can use sklearn for doing this. Yes. The other part of this basically is I told you about the gradient descent. Yes. You could also design your own linear regression from scratch. Yes. That is both a good idea and a bad idea. Yes. A good idea because you will learn how exactly gradient descent works, and good idea today because linear regression is very simple. We can learn how gradient descent works. Bad idea because a lot of people have already put a lot of effort in making your this model, right? Beating linear regression from sklearn linear model will be harder. A lot of thoughts that you would think, okay, I can make linear regression better. They all have already thought about it, and people have already contributed to the library. So it almost always will outperform you. Okay. At best, you could probably match it unless some domain knowledge comes from you. Fine. But as a goal from our side, we can, of course, design a linear regression from scratch so that you understand what are the paths playing into and how exactly we find W and B. And one of the algorithms that we could use is basically gradient descent. Yes. Overall, it will look it will look a bit longer, but it's simple enough. Yes. We'll go through it. And let's say create a linear regression from scratch. Fine. This is a code completion. Please forgive me. But this is useful. That's why we're using this. Yeah. Fine. Excellent. I'll just go through if this is written correctly or not. Fine. So what we are doing is if you understand Python or any other thing, generally what we do is generally define classes, and classes can have objects. The usefulness of classes is basically each class can have multiple functions in it. So all the functions together can make up one particular class, and this particular class we can create multiple objects and call them again and again. Yes. And each particular object has its own memory space. So it's wonderful, right? Rather than just writing functions, we could have written just a function also. Yeah. Fine. Okay. So here, if you remember that function, give me a minute. Sorry. If you remember it was FWB. It is not in LaTeX, so forgive in that sense. We want to find out Wx plus B, and again, every time the W gets updated, I hope you remember, W will be equal to, let's say, weight minus the gradient, right? This is what we want to do. So we have a function f of x, b, which is wx plus b, and every time we look at something, we will first find all the average losses, and after we find all the average losses, that will basically give us. Then we take a derivative over that particular x. We'll find the gradient, and then based on that value, we can do a subtraction. Okay, and the new weight we can find, and similarly we can do for bias also. That is the good. And we don't exactly subtract the directly gradient. What we do is we do a alpha multiplied by the gradient. I hope you remember the slides. So that is the learning rate. Yes. So here what we are choosing, if you see it's a definition of init, it basically says my learning rate by default is 0.01. So instead of doing gradient as a whole, I will do at a time I will subtract the weight, or I will move the weight to the actual value of weight, or to the optimized value of weight by 0.01 method. Yes. And how many times you want to continue this exercise of updation. In the slides I have written till it converges, but sometimes convergence can take a very long time. So here we can actually stop at 1000. Yes. You can also design your own algorithm that will only stop, let's say, whenever only when it matches. Okay. But there are cases where convergence is not guaranteed, right? So there are cases, but we are not discussing that today. So now that is the goal. Yeah. So we have initial classes. Init class are basically the initial definition of any particular class. If you take, that is the base function we can have. Here we decide basically all the variables that we'll use. Yes. So we have a learning rate, we have iterations, we have a weight and bias. Okay. This 0.01 1000, those who have done Python, it's super easy. What it says that if you don't pass me any value, by default I will take 0.01. If you don't pass me any value on iterations, by default I will take 1000. Yeah? And then we also declared weights and we declared the bias. Yes. Now following this, we declare another function called fit. Yes, fit, remember, this is equivalent to this particular fit that we want. Yes. And the fit here takes the input x train and y train. Similarly here also the fit has to take some x and some y. Now the goal is what? So we have to find out how many samples are there, how many features are there. Based on that, we will create. Now, initially, if you see, I have wx plus b, but what should be the initial value of w, right? So let's say the final value of optimus value is 1.2. If I start with 1.2, well and good, but I don't know what is 1.2, right? Like I don't know that optimal value of 1.2. So I could start with any other random possible value. There is a lot of theory behind what is a good random start, or also what's a good initialization of weights, but not today. Yeah, probably not even in this course. Yeah. But we can here, because it's a very easy problem, we can start with zeros. And here, if you see, we have started to use NumPy. Yes. Let me just run this to see if there's no error. Yeah. So now what does this create? NP dot zeros and n features. Anybody? Okay, but anyway, so this is not a chat. So np dot zeros will create basically a NumPy array with all the zeros, and the size of that NumPy array is number of features. X dot shape basically gives me like a lot of values, but here it gives you how many samples are there and what is the dimension of X, right? If I pass X dot shape will be giving me how many samples. So it will look like a matrix. Yeah. So if the number of dimensions are D, it will give me like D features, and the number of examples I have, let's say it's N, that will go into the samples. Yes. Once I have this, I have declared my weights, starting weights as 0. Then the bias can be 0 again. Then we go to our gradient descent algorithm, right? Gradient descent algorithm is basically this, right? So first we find my bad. Yeah. First we do a prediction with, let's say, FWB. The moment we find prediction, we find what is the loss. Yes. So that is basically Y prediction minus Y true, and this guy is whole square. This is just the loss function, but if we want to do the cost function of this one, then we have to do, let's say, average of this, like our empirical loss. Yes. And we have to calculate gradient on top of it, right? So but this is the loss function. Yes. Now what we can do is, first then the goal is to calculate the Y prediction. So we calculated Y predicted. How do we calculate the Y prediction? It is basically x fx, but this fwx plus b. We are doing exactly the same thing, right? It's just multiplying the x with the w plus doing the bias. Np dot dot is basically multiplying two vectors. Yes, for us. So this is Y predicted. The moment we have Y prediction, we can compute gradients. Either we could have found the basically loss and then the gradient, or otherwise we can just calculate gradient directly from this, right? So the gradient with respect to X, let's say, or sorry, with respect to W, because W has to change, will be the like delta of that loss with the delta of W, which eventually comes out to be this, right? This is equal to, of course, a gradient with respect to weights. Yes. If you do the derivative, it will come to this. So what we are doing is basically multiplying np dot with the y predicted minus y. Yes. And multiplying with the x. Yes. And then, of course, we are having the taking the average of that. And similarly for the like bias, it will be just this, because the first term becomes constant, because for the bias the w and x both become constant. For, of course, for w this becomes constant. Yes. So now that we have this, and this one we place because we are trying to find, just to give a little bit more clarity, I am trying to find dws by dw, yeah, which is equivalent to this. It is like 2 by n xt and then y prediction minus y2. It's basically taking this derivative with respect to dw. Y prediction expands to wx plus b. Based on that, we are calculating this. Okay, fine. So now we calculate the gradients. Now we have to just subtract this gradient from the weights. Instead of doing a direct subtraction, like weight minus the gradient, we are taking learning rate and then the gradient. Yes. So that's what we have done. So we just multiplied the learning rate with the gradient weight. Yes. And similarly, we have done the learning rate with the bias, and then we are just subtracting those. Yes. Excellent. And then we define another function called predict, which basically is this particular, which just basically multiplies whatever we have, weights we have found, bias we have found, just the doing. This basically thing. Okay? Y predicted. FWB takes an x and plus b. Okay? Wx plus b. This is the one that we were doing it here. Fine. So this is a simple class for doing a simple linear regression. And mostly what sklearn also has is very similar to this. All of you are free to go and check the source code of sklearn. That is also freely available if you go to the sklearn's website. Now that we have this defined, so the next step is to use this. Yes. Now what do we do? So the class is done. Sorry. This one. Okay. Okay. So now that we have defined a small class that can do linear regression, the rest of the method goes very similar because we have defined the similar function. So we have defined a fit function here, which basically will take the input x, input y, and then do the model fitting. Model fitting here is basically finding the optimal value of w and b. Here we are restricting the number of iterations to be 1000. We can make it larger also. Okay. Uh, then the more you make the iterations, most likely it will go closer to the actual value, 1000, 2000, as much as you can try. More number of iterations you do, the more time it will take. Yes, but these are linear regression, very easy stuff like a single to single. The one that we have chosen is one-dimensional data. So yeah. So we have done exactly the same thing. So if you look at the, let me just copy this one for you. Okay. Yeah. So if you see the top one is from sklearn, and this is the one that we are using, the custom that we created. So if you see the same principle, we declared a model that comes from the linear regression. Here we declared a model that comes from the our class that we defined here, simple linear regression. The moment we define simple linear, here we are accepting to these values. The linear regression will also have something like that, but for now, let's keep it. The next step is we declared model.fit. So we called the fit function, which basically finds the optimal value of W and optimal value of B. Here also we are calling model scratch, fit, and this one. Then we also had a predict function. Similarly, sklearn also had a predict function. Our predict function just takes a particular x and gives us the y prediction. We found it the same thing. Then we again calculated the R2 score, how much it is better than just predicting the mean. and then we rate it. So it is coming 0.94. The sklearn was also around 0.94. Yes, because these data are like very close. So we are also very close. Yes, sklearn also uses the similar algorithm, so we are super close. Fine, and we can. So we can. Oh, sorry. We can do the exactly same scatter plot here also. We can also see, and it will be also looking equivalent to this plot. Yes, true values, prediction, and the regression. If we plot, the same thing will come up. Yes. The only thing is I have not written the function to give the x and y, that we will have to write it up here. Then only it will give us the particular w and then b. That's what we require. Hmm. Fine. So I hope this is clear then. So let me just reiterate what we did. Fine. So from the machine learning point of view, there are few major fundamental algorithms: linear regression, logistic regression, SVM, KNN, and if I'm missing something, then that is there. A decision tree, yes. And then today we study linear regression, some of the important terms like loss, yes, empirical loss, what is a loss function, what is an average loss. Following that, we decided why it is supposed to, why should you take a square error loss? Why can you take absolute loss? Why not cube to the power 4? Of course, all of them make sense. All of them will create different kind of algorithms. Linear regression particularly, it has to be a linear relationship plus it has to be a square error loss for right now. And then we come up here and oh sorry, just going back, linear regression is very useful if because it already has an inductive bias. That means already doesn't matter what the data is, it will always assume there's a linear relationship between x and y. So that has to be taken into account. If your already data already has a linear relation, please take into account and use linear regression. Otherwise, doesn't matter how much you train or not train, linear regression will never give you the right answer. Then we went down. So we wanted to use, let's say, I wanted to show you very basic implementation of linear regression, which you will use for other algorithms as well. One of the libraries that is very useful in doing programming for machine learning is sklearn. So the way is you have to install scikit-learn. Again, environment, you have to make sure you're doing it correctly. You create a data set. There are multiple functions like that. There is a matplotlib to view this function. Training and doing everything is just simple this, right? This is the one that trains, the one that I've highlighted, model.fit. That is the one that does training for you. Yes. And you can do another, like you can use matplotlib to plot true values, prediction, all this stuff. And if you fancy yourself, you can also write your own linear regression and not depend upon other libraries. Yes, that will require you to learn NumPy and to understand some portions of gradient descent. Yes, I will share this notebook with you so that you can use this as a startup again. Yes, but anyways, I think most of you will connect Copilot hopefully, and then code completion will help you. Not an issue. Please use it, but make sure you understand what it is writing. Sometimes it will write wrong things. Yes, sometimes it will write logistic regression, and you are expecting it to write linear regression. Yes, but don't do that. Other than that, it's okay. If you know what it is doing, then it's fine. And remember what we did, the gradient descent is gradient descent we will keep on covering as we go again and again. So even if you don't understand fully gradient descent, not an issue, we'll keep on covering. But what I wanted to say is that we could also write from scratch. We could also do this training with the fit function if we write it fit. Here, if you had written some train function, of course, here we have to write train. This fit and train is coming from the separate class that we define. But sklearn already has its own fit function, so you have to use fit. We cannot write train there. And then once you do that, and then because data can go high dimensional, we use metrics to find out, to evaluate between two particular algorithms. For example, if ours gave 0.93 and sklearn's gave 0.94, we can clearly tell, okay, sklearn's 0.94 R2 score is way better than ours. Yeah. And that's all. That's all for today. I hope linear regression how to use NumPy and NumPy to write your own scratch code, and then how to use sklearn to use sklearn's libraries algorithm to again train your model and test it. Fine. Okay, that's all for today. Next class we'll touch logistic regression and similar principle. We'll study the algorithm, we'll write the code. Okay. Every time while writing the code, I will focus on few of the parts so that by that you please practice. Huh? All of you please practice if you have specifically have no idea before. Fine. If there are any questions, I am here for 5 more minutes. Otherwise, we'll close this.
Okay, sir.